Parametric equations. So an introduction, a basic introduction to parametric equations, just like we did a basic introduction to polar equations. These are parametric ones. Okay, so we're going to look at plane curves and parametric equations. We're going to work on eliminating the parameter, finding parametric equations for a curve, and then using graphing devices to graph some of these guys. Just like before, the easy ones we do by hand, and then they very quickly get complicated, so then we want to use technology to help us graph them, but we want to get a good idea of what's happening. Even if technology takes over, we have a sense of what the technology is doing. Okay, so parametric equations. We can think of a curve as a path of a point moving in the plane. The xy coordinate of that point are then functions of time. So this idea leads to the following definition. So if f and g are functions defined on the interval I, then the set of points f of t and g of t is a plane curve with these equations. Right? What in the world does all that mean? What this means is that we're going to be looking at situations where the ordered pairs that we're graphing are themselves the outputs of different equations measured by a third constant, which is usually t, and we often refer to it or let it be equal to time. So we'll have, for example, let's do a really quick one. There's like, well, I guess there's a nice example there. Okay, let's just jump to this example. So what we have here is a case where we have ordered pairs that we're going to graph, and the input variable is the x usually, right? And the output is the y. But now, instead of letting x just be any value that you can choose, the independent variable within a certain domain, the x coordinate is itself going to be the result of an equation, where the equation is an equation written in the variable t. And the y is also an equation written in the variable t. Good. So the t is called the parameter of these guys. So in order to graph this, we're going to have to create, if we're going to do it by hand, we're going to have to create a table of values. So let's begin with creating a table where we have t values, and then we have our x, which is equal to t squared minus 3t values. And then over here, we'll have our y values, which is t minus 1. So for example, when t is equal to, let's put it right over here, 0, let's get rid of the 7, then we end up with x equals to something squared minus 3 times something, and y is going to be equal to something minus 1, and that something is a 0, 0, and a 0. We end up with x equals 0. It's going to be 0 squared minus 0, so this is just going to give you a 0. And y equals to negative 1. So we end up with this ordered pair, 0, comma, negative 1. As our first ordered pair that we graph. Okay? When t equals to 1, then again, we have to first of all crack the code for the x coordinate. It's something squared minus 3 times something. And the y is equal to something minus 1. And that something is our parameter value of 1, 1, 1. And so we end up with 1 minus 3. So x is going to be equal to negative 2. X equals negative 2. 1 minus 3. And y equals to 0. So we end up with the ordered pair, negative 2, comma 0. Good. We can also let t be equal to a negative value, about negative 1. So then x equals blank squared minus 3 times blank, and y equals to blank minus 1. And then we let this be negative 1, negative 1, negative 1. So that becomes positive 1 plus 3, so x equals to 4. And over here we end up with y equals negative 2. So now we have the ordered pair 4, comma, negative 2. Okay, so far we have 3 points, and when we don't know anything else, we just keep going. Find more values of t. So I'm going to continue in the same spirit. I'm just going to use technology to continue to create this table and then graph these ordered pairs. So I'll just use Desmos for that purpose. Okay, so let's create some tables. And t, and then the first one was t to the second power, t to the second power minus t, minus 3t. Minus 3t. And the next one was t minus 1. Like this. Okay, I want to graph these guys. I want to graph this. Okay, so for example, when we had a 0, we had a 0 and a negative 1. Yep. When t was 0, we had a 0 and a negative 1. And when t was -1, we got a 4 for the x coordinate, and we had a y. Okay, so these are my x and my y's. Okay. And then lastly, when we had a 1 here, 1, we had -2 for x and 0 for y. Okay, so then this is helping me figure out all my x coordinates and my y coordinates. Now, I wish I knew how to graph these two as ordered pairs on Desmos, but I don't, so I'm going to have to do an ugly little trick here of just coming back over here and just putting these as my x and my y and just kind of manually typing them in. 0 there, -1 there. And now it should graph that point. So 0, -1 becomes this point right there. There, I have 1 point on my grid, right? Okay, not good enough. I got to keep going. Okay, another point on my grid would be 4, and then a -2 here. Good. Okay, now I have 2 points on my grid. What about -2, and a 0? Okay, so now I have 3 points on my grid. Got to keep going. Okay, so let's keep going over here. How about 2, 3, 4? Okay. All right, so then this is 0, 2 is another point on my grid. 4, 3 is another point on my grid. Okay, so I'm starting to see a bit of a pattern, maybe. Let's try a couple more. How about some decimal values? How about 0.5? 0.5 will lead to -1.25 for my x-coordinate and -0.5 for my y-coordinate. So that leads me to another point there. How about if I do 1.5? 1.5 will lead to -2.25, and then the output would be +0.5. Okay, I'm starting to get a better sense of where this is heading. How about 2.5? How about 2.5? How about 3.5? How about 4.25? Okay, so this is going to be -1.25 is mapping with 1.5. That gives me another point there. +1.75 maps to 2.5, and also 5.3125 leads to 3.25. Okay, there. So by hand, pretty painful, but we've started finding these values, right? And it's starting to look like a parabola on its side, maybe, right? And of course, if I wanted to do it by hand, keep going, I can find some more points, and eventually, I would, I think, convince myself that this thing is going to start looking like a parabola on its side. Good. But also, not only do we get a shape, but notice that we get a direction as well, right? As we graph these, this one was the result of. How did we get this as the result? We got this one from -1. Good. And then this one was the result of 0, -1, 0, -1. That's this one. Right. These should have been in the other order, but okay. And then this one was the result of 0.5. Right. So if I ordered these in order, the smallest one is -1. I tried it for -1, -1, then 0, then 0.5. Then 1.5, then 2, then 2.5. And you notice that as t increases, we're going to get this value, then this value, then this value, then this value, then this value. So there's actually a direction that has to happen. This one was the result of using -1. This one was the result of using 0. Somewhere in the middle will be the result of using -0.5. Let's confirm that. If we go back over here and we type in -0.5, we get these ordered pairs, and now if I graph those ordered pairs, I get 1.75 and -1.5, and then we get this guy. Okay, so as t increases, here's 0. As t increases 0, 1, 2, 3, 4, 5, to infinity, it's going to create this part of the parabola. And then as 0 goes down toward -infinity, it'll create this part of the parabola over here. Any questions about that? Maybe, sort of, kind of. Maybe, sort of, kind of. Okay, so here's a better picture of the whole thing. We create a table with t values, resulting x values, resulting y values. And as we graph them, we'll end up getting all these ordered pairs that will eventually fill up so many that it ends up looking like a nice, pretty, solid curvature, but it's not, right? It's an infinite number of little dots that are all associated with these. And also you see that there ends up being a direction as well. -2, t equals to -2, t equals to -1, t equals to 0, t equals to 1, 2, 3, right? And then all the little decimal values in between. So when we use parametric equations, not only do we get a shape, a curvature, but we also get a direction along that curvature. Right? We get a third, we get more information. Good? Good. Questions? So as t increases, a particle whose position is given by the parametric equation moves along the curve in the direction of the arrows. Right? So the little direction of the arrows is important. It's an important element of parametric equations. If we replace t by -t in example 1, we obtain the parametric equations here and here, right? What were the original ones? The original ones were x equals to t squared minus 3t and y equals to t minus 1. So if we replace each one of these by a negative t, get x equals to -t squared, well that's just going to be t squared, minus 3 times -t, that's going to turn it into plus 3t. And then over here we end up with -t minus 1. So the graph of these parametric equations, okay, so now if we graph these guys, we end up with, the graph of these parametric equations is figure 2, so that's this one over here, and you get the same curve, but traced out in the opposite direction. Good. So replacing t by -t is going to give you the exact same picture, except that here it traces in this direction, right? It goes this way, and then that way, and then that way, as t increases from -infinity to +infinity. Whereas this new set of parametric equations, all it does is change the direction along that same curvature. Good. Questions? Okay. On the other hand, if we replace t by 2t in example 1, we obtain the parametric equations here and here. Right? So again, that equation is just found by looking at y equals to t squared minus 3t and replacing each one of these by 2t. So we get 2t squared minus 3 times 2t, and that's how we get this equation here. And then the other one was y equals to t minus 1. So if we replace the t with 2t minus 1, we get that. And so that's how we get that equation. Okay, and notice that, in fact, we get, again, the exact same shape. The picture, the graph hasn't changed. But what happens is we trace through it faster. So we just go through it in a faster way. The graph of these parametric equations is, again, the same, but traced out twice as fast. So that's what happens when we replace it by twice t. And if we replaced it by 3t, then it would trace it out 3 times as fast. Good. So thus a parametrization contains more information than just the shape of the curve. It also indicates how the curve is being traced out, the direction and the speed in which the curvature is being traced out. Okay, manipulating these guys. So we could eliminate the parameter and put it back into our standard Cartesian coordinate system. And there's different ways to do that. The most common way is to just do the substitution method. So eliminate the parameter in the parametric equations of example 1 by the substitution method. Okay, so example 1. So if we had x equals to t squared minus 3t, and then we had y equals to t minus 1, well, pretty easy. What we could do is just take y minus 1, make y plus 1 equals to t by adding 1 plus 1 plus 1 to both sides. Come on. And now we can take this t and plug it right into there. Right, so then this becomes x minus blank squared minus 3 times blank. And we're going to take this t value and dump it in there and dump it in there. So now t becomes y plus 1. And here we get y plus 1. Good. We can simplify it a little bit. X equals to y squared plus 2y plus 1 minus 3y minus 3. And so x equals to y squared minus y minus 2. Okay, y squared minus y minus 2. Good. And so this is a parabola on its side, which is what we expected. Good. Questions, questions, questions? Yeah, we could do more with this if we wanted to figure out all the information we wanted to. For this guy, we can complete the square. Right? We write this as minus y, and then half of this squared, right? So this number right here, minus 1, it's minus 1 times 1/2 squared is the perfect thing to add and subtract. That's going to be minus 1/2 squared, which is equal to positive 1/4. So we'd want to add 1/4, subtract 1/4, right? Minus 2. Then that guarantees that the first 3 terms are perfect square trinomials. And so this is going to be equal to y minus 1/2 squared. And then we have this minus 1/4 and minus 2. So as a mixed number is minus 2 1/4 as a mixed number. But then we don't want to leave mixed. This is a mixed. So then x equals to y minus 1/2 squared minus 9/4. Okay, so now that we got it into this form, we can see it's a parabola. You can see the vertex. Right? It's got a vertex at 1/2 comma negative 9/4. But we have to be careful that this thing has been switched, right? Because normally, right, in the normal input-output relationship, we would have it the other way around. Y equals to x minus 1/2 squared minus 9/4. So it's kind of similar, but we're just changing the axes, right? So the vertex of this one is 1/2 comma negative 9/4. But we have to reconsider how that adjusts to this thing. Good. Let's see what the author did. Replaced +1, -1, +2. Oh. Example 1 has a rectangular equation of minus y minus 2, so it's a parabola. Okay, author just stopped there. Minus y minus 2. Minus y minus 2. Good. Okay, any questions? No? No? Okay, so sometimes you'll be asked to find the parametric equation. So find the parametric equations for the line with slope, for the line of slope 3 that passes through the point 2 comma 6. Okay, so it's got a line, it's got a slope. So roughly speaking, we can do a rough little sketch. There's a point at 2 comma 6, I don't know, somewhere around there. And there's a line that goes through it that has a slope of 3. So let's make it in blue. I don't know, maybe something like that. So find the parametric equations for the line of slope equals to 3 that passes through this point. Okay, so remember that every dot on here is an ordered pair, right? And in rectangular coordinates, it would be x comma y points, right? And one of those points is the point 2 comma 6, since that's that point right there. So we need to come up with an equation for the x and an equation for the y that maintains this relationship. And that relationship is determined by the slope. The slope is this guy. 1 unit here, 3 units there. So whenever the x is changed by 1 unit, the y is changed by a multiple of 3 units. Right? So in general, if this thing is changed by t units, then this thing would be changed by 3t units. Whatever this value is, we triple it, and that's what we get there. Good. However, we have a starting point of 2, so from here I can conclude that the x equation has to be 2 plus t, and the y one would be equal to 6 plus 3t. Good. Let's check and see the first point. The first point at 0, at t equals to 0, we would just get 2 comma 6. let's find one more point. If the slope is 3, then this point over here should be 3, 9. Right? We go out 1 unit this way, 3 units that way, so the 2 changes to a 3, and the 6 goes up by 3, goes up to a 9. So now if this is a 1, if t equals to 1, we get a 3. If t equals to 1, we get a 9. Yeah, that seems to match. Good. So here is our parametric equation of the line that has slope of 3 and goes through the point 2, 6. Any questions? Questions? And yep, that's what the author did as well. 2 plus t, y equals to 6 plus 3t. And we can check it by doing our substitution thing one more time. Check. X equals to 2 plus t, and then y equals to 6 plus 3t. Well, the easiest thing to do is to solve for t here. So x minus 2 equals to t. And now that's what we're going to come over here and plug in. Y equals to 6 plus 3 times something. And here is we're going to stick in our t value. That t value is x minus 2. So we end up with y equals to 6 plus 3x minus 6. The 6's cancel, and we get y equals to 3x. And that is a linear equation that has a slope of 3. Okay, linear. The original statement said find the equation of the line, so we were expecting the linear equation with a slope of 3, and then just confirm that it also goes to the point 2, 6. So if x equals to 2, get y equals to 3 times 2, which is 6. So it goes to the point 2, 6. So yeah, it gives us the equation of the line. Got it? Got it? So in rectangular, I could say y equals to, here's a nice little graph for it. So in rectangular, I could say y equals to 3x, right? And that's going to give me that red one, that red line. In parametric, in parametric form, I would have 2 plus t and comma, oh, that looks ugly. 2 plus t, comma, 6 plus 3t. It'll still give me the exact same graph, except it'll give me even more information. Right? This guy, the way it's written, also indicates that we have a direction. Starting at this point, it goes that way. When t equals to 0, it starts to head that way for larger and larger values of t. And so therefore, we have a direction that goes like this. As we saw right above, we can also manipulate these equations to change the direction. If I wanted to make it go in the opposite direction, then I would just have to change all the t's to negative t's. If I want to trace through it faster, I can multiply a constant times the t value. Okay. Any questions? Okay, and then graphing, like I said, these are really hard to do by hand, so right away we really want to depend on some of our technology to graph some of these things. So let's graph one of them in Desmos first, and then we'll use our calculators to graph these. So use a graphing device to draw the following parametric curves, discuss their similarities and differences between the two. Okay, so let's look at, well actually, I don't know if, yeah, let's just go to our calculator. Okay, the first thing we want to do when we get to our calculator is go over to where it says mode. And now we had polar, right? We normally work with functions. We just work with polar, and now we want to go here where it says parametric. So go down, down, to the right, down, to the right, parametric, hit enter, and now the calculator knows we're in parametric form. Okay, all right, so now if we go over to y equals, now it'll give you an x sub 1 and y sub 1 t for each little grouping. Now it knows you're in polar. You need an equation for the x-coordinate, an equation for the y-coordinate separate, right? And they're both going to be functions of t. So the x-coordinate, let's type in sine 2t, right? And that same button that used to have an x, and then later when we did polar, did a theta, now it does a t. Right? The calculator knows that you're in parametric form. Good. So now we want to do 2 times cosine of t, like this. Good. Next, let's go to our window, and now we have to give a range for the t values. Good. Now, t values happen to also be angles in this, right? Because we have cosine of something to the domain. The thing you plug into a sine function is an angle. So 0 to 2 pi seems appropriate, an appropriate place to start, see what happens. Good. Now, for the x and y, that's going to be a little trickier. Okay, so the x coordinate is going to be bounded between -1 and 1, right? The sine function is bounded. The y coordinate is going to be bounded between -2 and +2. So let's just pick some values. This should be fine for the x, and let's make it -3 to +3 for the y, just to make sure we capture everything. We can always come back and guess and check different things. So graph it, and we get that. Like an hourglass symbol. Any questions, any questions, any questions? No? 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 Okay, they also give us another pair over here. Let's go back over here. Now, I don't want to erase these right now, so let me just highlight the equal sign, hit enter, and then it'll unhighlight them. See how they used to be dark? That means that the calculator will continue to save those equations, but it's not going to graph them. Okay, so now if I try the other one, sine of 3t, and then 2 cosine of t, close. Now let's graph that one. Okay, we're going to leave it for the same window, and we get that. Good. Questions, 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 questions? How to graph it? Okay. So in both parts A and B, the graph will lie inside the rectangle given by -1 to 1, right? That's because the sign is bounded by -1 to 1. This 2 or this 3 change how frequently we complete a period, so it oscillates faster through its period, but it doesn't change the amplitude of the sine function. It's still trapped between -1 and 1. And this 2 right here changes the amplitude, so it's bounded between -2 to +2 for the y coordinates. Good, good, good. Since both our sine and cosine numbers lie between -1, okay. So we tried that rectangle. Okay, so there you go. You just have to use your technology to graph it. That's all these questions are going to ask you to do. Right, so we know that each one of these little points on here is an input-output, an x comma y, where the x is actually this equation and the y is the result of this equation, both of them being manipulated by a third variable that's not in my grid here. It's the t variable, right? The t parameter. And the t parameter, in this case, is ranging from 0 to 2 pi. Good. And then we got this one for the other equation. Good, good. Both graphs are closed curves, which means that they form loops within the same starting point and ending point. Also, both graphs cross over themselves. Right? So these are similarities between the two. However, the graph in 12a has 2 loops like figure 8, whereas the graph in 12b has 3 loops.